This picture here is of a morpho butterfly. If you look closely at its wings, this blue color actually tends to change color a little bit and shimmer as you look from different angles. This indicates that it's not just a dye, but something more complex that's going on. In fact, it's an example of interference, which is one of the key ideas of wave optics. So here in chapters 35 and then in chapter 36, we're going to be focusing on interference and wave optics. Not wave optics, wave optics. This is aspects of the behavior of light that cannot be explained simply by treating it as moving in a straight line in a ray model. This will be key to understanding a wide variety of phenomena, including why you see colors on oil slicks and how non-reflective coatings on glasses and camera lenses work. Now, the first good model of wave optics was by a man named Huygens. It doesn't take into account the full vector nature of the electric and magnetic fields, but it does get most of the key wave properties. And one of the key ideas he said was something known as Huygens' principle, which is that all points on a wavefront serve as point sources of spherical secondary wavelets. In other words, if I've got a bunch of waves here, so this is a wave advancing, any point on any one of these waves could become the source for new spherical waves, known as secondary wavelets. So for example, if I were to take some kind of a big barrier here and block them out, these waves here would cause the space in the center to move up and down, and that, if these were waves on water, then the waves would come in. The points here in the center would be moved up and down by the waves coming in, and that motion up and down would cause waves to bend as they came out. Now that principle works well for any kind of wave, but Huygens in particular applied it to light waves. So for example, can that explain the fact that light moves forward in nice straight lines? Standard ray optics approximation that a plane wave moves forward in a straight line. Absolutely. So here we have a wavefront at time t equals 0. And we imagine that each one of these points becomes the source for a new wave that we see illustrated here. Okay, so this one is the source of this wave right here. This one is the source of this wave right here. So we imagine each of these sending out a spherical wave, but at a time delta t, sometime later, they all reinforce one another, add up constructively, and we have constructive interference here, where the wavefront should be a time delta t later. So just by adding together the spherical waves, we get the plane wave moving forward as we expect it to.